starting now. Okay. Wait for the green light, and then you'll know we're going.
We have made the unhackable hackable, and we've made the hackable unhackable.
It's time to wake up, universe. Hello, everyone, and it's time to wake up, universe. Go outside, go smell the roses, or even better, learn about computers. So today, we will be talking about quantum computing, but while we're at it, let's start talking about kinetic energy. Kinetic energy. Now, how does kinetic energy work? Now, let's explain all about pressure and temperature.
What is pressure, first of all? We need to understand
What
that.
is pressure?
What is pressure?
Pressure is quite interesting. As you may see on the board above, pressure is actually just kinetic energy. You can see this balloon that I have drawn there, which is actually what we have here. I have a balloon on top of a test tube, and I have a Bunsen burner. Now again, if you are to perform any burning experiments at home, please do have adult supervision, because we don't want you to get hurt, but just to show proof of concept. You see, in a picture above, I have a balloon, and this balloon is expanding. Now, I'll get more onto that later, but the idea of kinetic energy and pressure. You see, pressure, think of your tire, for example, your car tires. When you fill this balloon up with air, you have the air consistently moving around and banging the inner surfaces of this. Now, what do you have to say about that?
Well, first of all, I can tell you one thing. With the pressure, if you put enough pressure and all those molecules hitting together and hitting the sides, you create, it blows up, basically. So it depends how much you put in there, but...
See, pressure can do a lot more than just fill a balloon. I mean, there's so much. And just the laws of partial pressure, thanks to Mr. Dalton, and thanks to Graham's law, we can think all about rates based on pressure. Now, getting more into that, let's start the flame here.
Now, kids, don't try this at home. Just want to make that clear. You don't play around with this.
So we're going to start the gas.
Right here we have, as you will see here, we have a blue flame. This is a Bunsen burner. Do not touch the flame. It will burn your hand off. But it is time to see what's going to happen. As you can see, we have tiny little bubbles coming up.
So we'll stop worrying about that guy for a minute, but just getting more into this. So, just to explain, today we are talking about quantum computers. Now, to get into more about what we were saying, making the unhackable hackable and the hackable unhackable. So, as you can see on the board above, you may know about traditional computers. Traditional computers use traditional bits. Now, these bits are either 0 or 1. And as you might see on the right-hand side, we'll talk more about transistors later, but transistors are essentially just switches. They're either connected, so current is flowing, or they're disconnected, so current is off, just like the light switch on your wall. You can turn it off.
Go ahead. And that those switches and everything, that is the reason that why we can transmit information, whether it be a cell phone call, whether it be a computer, whether it be whatever. It is by that we can transfer information, by those little switches.
That's really interesting to think about. But the combination of all of these different zeros and ones is the order in which we write code. It's the order in which data is written. And so the data that is stored in your computer, all the information that you've put on your computer, is the reason for a lot of different things. It's based on these zeros and ones, based on, now your computer is composed of many transistors, lots of them, so lots of different zeros and ones create the answer. And so getting back to that, you can see on the board I have a combination of 2 bits. Now there are 2 to the n being the number of bits you have, 2 to the n possibilities of combinations of bits.
And in English, that's a lot of possibilities. A lot.
A lot. You see, let's think more about this. So thinking about this in a little bit of a way, you look on the board there, I have 2 bits, 2 to the n equals 2, right? We have 2 different bits. Now, I guess we're going to cut that off for a second, because I'm going to exemplify.
What's happening here? Oh my. Look at this.
Show you. The balloon is expanding. Pressure is expanding, you see, because here's what happens. At a higher temperature, now I am going to turn this off before the balloon decides to pop.
That is true. We don't want that. But you can see
and so you can see that the balloon had expanded. Now, why is that? Let me tell you something. A liquid, it really depends. Now, you can say everything in this room is room temperature. Mm-hmm. This table, which is a solid, and the liquid in there, which is water. Now, water and this table right now, because they're the same temperature, they have the same kinetic energy. The higher the temperature, the higher the kinetic energy. So what we did is we heated up the water there, and we gave the molecules more kinetic energy. Mm-hmm. So what happens when you give something more kinetic energy? Well, kinetic energy is the energy of motion. Mm-hmm. In this case, it's the motion of molecules. And water vapor, what does water vapor do compared to a liquid? Water. Water vapor has a lot more motion. Once you give something more temperature, it moves a lot more. When something has more temperature, it moves a lot more. So how does more motion inflate the balloon with steam?
You need to think about it in this way. Picture you have a 1,000 or a bajillion little pieces of matter basically bumping around. The more energy that they have, the more that they're bumping around, and they're bumping around, they're trying to expand. That is what happens when there's a lot of mass in a certain area, and with enough temperature, it will try to expand. It will try to go to other places where there's not as much. So it will hit against the sides of the balloon, and that is why we have this little baby right here.
Expansion. Ooh. And that is the really cool thing about this. Now let's explain more about how this has to relate. Back to our bits. Now hold that thought in mind, because we are going to explain why kinetic energy has to do with what we're talking about. So if we think more about those bits again, 2 to the n different possibilities for 2 different bits. Why? So think about that. Look on the board. How many ways can I write a combination of zeros and ones? Well, when there's 2 bits, it's 2 to the n. 2 to the 2 is 2 squared. 2 squared is 2 times 2, which is 2 to the 4th power. I mean, what am I saying? Sorry. 2 to the 2nd power is 2 times 2. 2 2's, which is why I said the 2nd power. So that makes it 4, right? Because 2 times 2 is 4. So let's think about that a little more. There's 4 different possibilities, right? We have 2 bits, so there's 4 possibilities.
It could be any one of those possibilities, but we need to have the answer right now. So what happens? How does that work?
Let's explain more about that. See, because with 2 bits, you can have 4 different combinations. You can have it be 0, 0, 0, 1, 1, 1, or 1, 0. Of course, because you have 2 transistors. 2 bits is 2 transistors. Because there is either current flowing or no current flowing, which is 0 or 1, as exemplified on the right side of the board. So, talking more about this, look at the quantum side of things. On the left, your left, we have normal, traditional bits. 2 to the n bits. is the number of possibilities these bits can be arranged. Now just think about that. A regular computer, let's say you type in a password. Your computer has to go through every single one of those different possibilities to find which password is the correct one. You type in a set of numbers, there's all these different combinations possible to fill that password. And so your computer looks and tries all these different arrangements of bits until it finds the right one. Let's say in this case it's 1, 1, right? Now, qubits. Qubits can be 0, 1, or both at the same time. That is what makes 2 to the n bits equal n qubits.
And the impact of that on our daily lives is, I mean, without computers, a lot of things would not be possible. But the idea is that because of these little chips, our computers are able to run countless different algorithms at the same time, able to operate on such a molecular level that basically without those computers, without all that technology that we are using, what most, your cell phones. I mean, some of you kids have cell phones these days. And, I mean, I've got a cell phone, okay, I'll tell you that.
Don't we, all?
Oh, yeah, we don't.
Not all.
Oh, no, most people.
Most people.
Okay, kids, don't worry, it's not. Wait until you're older. But the thing with cell phones is, if it wasn't for all those different, electrons moving all around, that would not be possible. All of the things that we have today would not be possible. Your phone would not be possible. What do you think?
That is a really interesting thing to elaborate on. You see, it is based on the fact of these combinations of 2 billion transistors, 2 billion zeros and ones. 2 billion combination, 2 billion possible ways. Just think about that. 2 to the 2 billion. I'm not going to calculate that now because I can't do that in my head.
No,
that's a lot of possibilities. 2 to the 2 billion. That's a lot.
Ain't nobody got time for that.
No one has time to wait around for that. That's why old computers take longer, because they have fewer transistors. You see, older computers used to be large and bulky, and now we have things just as skinny as a MacBook Air, say.
Mm-hmm.
Now, think about that. Why is that? It's because we used to have to make transistors the size of wires. We used to have to actually have switches to be transistors in computers.
Mm-hmm.
And that realization, that combination of zeros and ones, thank you to Alan Turing for coming up with the first computer to figure out transistors, zeros and ones. That's how we can make bits. That's how we can take information. That's why they used to be so large. But we have shrunk and shrunk. We have made smaller and made smaller these transistors. That's where quantum computing takes it to a whole other level of how small something can be.
Mm-hmm.
Yeah.
With quantum computing, you see, it enables the entire world, the way that we operate. Basically, what if I could tell you that we could make your computer go 1,000 times faster than it is going right now? Go ahead. You can elaborate on this. This is something very important because this would change society as we know it.
You see, we use everything to figure out computers. And as we've made transistors smaller, we've made it so that the information, because physically being transported over a shorter distance, if you think about it. Let's think about that big physical switch on your wall. There is actually a piece of wire that is being connected or disconnected when you flip that switch. And so you're just taking this connection of wire because electricity has to flow in a complete circle, a circuit as we call it. Without a full circuit, a full connected circle, you can't have electricity. And so that's just the basis of a transistor. But think about it. Your switch, it has to travel through the distance of wire that is connected to that switch. And so when you think about what that means, we have made transistors smaller and smaller, making it travel over a shorter distance. And a shorter distance, well, that means faster, right? Just in general, you think about if something has to go a shorter distance, then it goes faster. It can get to its destination faster, just like the information in your computer.
And just like oh yeah, go ahead. Well, and just like the times when you run after your bus and you're running and you see it go away, it's very depressing.
You missed it.
Yeah, you missed it.
You weren't fast enough.
Nope, I wasn't fast enough.
But you see, with these computers, we'll make sure you leave on time.
Mm.
Here's why. So, let's look again at the qubit on your upper right there. The qubit. Okay, the qubit is not a combination of zeros and ones, really. It is a combination of 0, 1 at the same time. You see, 1 qubit, 2 qubits there, can cover all of the combinations at once. 2 qubits has so much, covers all the combinations at once. As 2 bits, there's lots of different combinations of 2 bits that could be as exemplified. 0, 1, 0, 0, all these different combinations. Well, forget all that when you can have all of that packaged in 2 transistors, 2 bits of information, 0, 1, and 0, 1. You see, you have 0 and 1 at the same time. Now, we'll elaborate more on why that is, but just think about it. Let's say your password is a combination of 2 bits, and the 2 bits are both 0. They have to be 0, 0. Or, right? So what your computer does is it has to go through all of these different combinations. It has to say, okay, is it 0, 1? No, it's not 0, 1. Is it 1, 1? No. 1, 0? No. Well, we finally get to 0, 0, which is your password. And boom, it finally picks it. It has to try all these different ways of finding the right answer. This is just the simple way I'm explaining with a password, but this is the same thing by typing in simple calculations on your calculator. But with a quantum computer,
everything changes, everything. You would get the right answer right away. Your computer would not need to go through all the possibilities. Forget that, that's old school. With this new thing, you could actually get the right answer like that. The computer would be miraculously fast.
Because you're trying them all at once. 0 and 1 at the same time. Combination of everything in 2 bits. That is what makes quantum computing insanely fast for all kinds of different algorithms. Let's think about Google Maps for a moment. Google's computers have to think about all of the different possible ways you can get from point A to point B until it finds
the shortest way. But just think about this. If I wanted to walk from here, from this side of the table to that side, there are infinitely many possibilities. I could go all around the planet and then walk over here. But that's not the quickest way. Google knows immediately I would go here. But the thing is, Jairus, you can explain.
Yeah, I mean, think about that. Now Google's computers, again, have to try all of these different combinations. And there's lots of different roads, right? There's lots of different ways to get from point A to point B. Ever seen a detour sign? Well, it's because the quickest way is blocked. It's in construction. So you have a detour, which is the next quickest way. And so instead of trying all these different ways, try them all at the same time with a quantum computer. That is one possibility. Let's think more about this, for example. Self-driving cars.
Ooh.
They are in range of our future. Your kids, my kids, are going to have... Your kids' kids are not going to have to get their driver's license. They're going to have to get their Switch license, I guess, because all they have to do is turn it on and type in their destination. Very simple. So, think about that. You're going to have all these different cars going around at once. You know, just think about that for a moment. Doesn't that scare you? All these different accidents. Well, if we have a quantum computer controlling every one of those cars, then there's no worry. Forget taxi drivers. We can have all these different, ways to get around with all these self-driving cars, and we can have a quantum computer managing all the different cars and realizing, oh, this car is going to hit this car needs to go in this lane, but this car does too. So instead, let's make this car, B car, we'll call it, go into a detour as opposed to A car, which has a different destination, finding the next quickest way or the next combination of bits, the next set of information that is the next best.
And the thing is, when we're talking about, kids or just people driving around in self-driving cars, there is no room whatsoever for mistake. If you make one mistake, that computer fails. And the truth is, nowadays, some of our self-driving cars, we've had mistakes, and the people have died. Yeah, exactly. And
That's why they're not on the road.
Exactly. And I'm not going to get one. But that's for another time. But the thing is, with a quantum computer chip, the car would not make any mistakes. There would be no mistakes on the highway. Unless something, terrible happened. But the reality is, the cars we would basically have zero accidents. It would be amazing.
I guess you think about it this way. It's like plugging in a whole bunch of x values into an equation. You can only have one right answer. Let's think about y-intercepts. Those of you who know about, if you think about it, let's go for the basic equation of y equals x. And we want to find the y-intercept. So what do? We find out where y equals when x is 0. So we plug in 0 for 0 for x, and we have to, let's think x plus 1 instead. 0 for x, okay? So what do? We subtract 1 from 0. We get -1. Y equals -1. Y can only equal -1 in a linear equation. A straight line. It only crosses y once. So the y-intercept can only be one value. But your computer has to try 0, 1, 2, 3, 4, 5, 6, all the way to infinite until it finds the answer where both sides of the equation are equal. And so that is another thing. Forget thinking about all these algorithms. Forget your calculator. Think about all the different ways to find the answer to your math problem when you can find it instantly. No different there is one combination only. And it covers every combination at once.
And you need to think about what this could mean. I mean, I know when I type in a problem into a calculator, in like a split second I have the answer. But the thing is, with the calculator, it's still very slow. And many of our systems nowadays, when we mention the unhackable and the hackable, our systems, they function at a certain speed, sometimes very quickly, sometimes very slowly. But the truth is, with this, instantly, that computer with the quantum chip would be the fastest in history.
Now elaborating more on, gonna have to talk a little louder. Sorry about the vent there. Elaborating more on, other than just the speed, possibility itself. So let's talk more about quantum computing. Well, let's talk about the transistor first of all. Transistor, we have two different parts. There are N parts and P parts. Now, with N parts, now we always use silicon. This is essentially the same thing as a switch, but we make it so it's really fast. This is modern day transistors. Modern day transistors use silicon crystals. They have 4 valence electrons, or the electrons in its outer shell. And we know that bonding between atoms, say for example, hydrogen and oxygen, right? For water. We have oxygen sharing electrons with 2 other hydrogens, which it also shares, right? What does this mean?
Well, basically, because of that fact, we have electrons that are basically the center of everything. If they fail, matter can no longer stay together. But with the transistors, we can actually use that to not just manipulate, but we can actually try to basically read information off of these microscopic events.
And that's the really thing. That's the really cool thing, is that you have these transistors and they transmit instantly. And so I won't necessarily elaborate too much on transistors right now, but later in the stream, once this is uploaded, I will put in the description the Veritasium explanation of transistors. Much better. He has a great video on how to explain them. But I'm just explaining the basis here, is that in the middle you have P's, which are what we call positive, describing the charge in electron flow. Now transistors went off. Let's explain. So because of the excess in a certain element, which bonds to the silicon, of electrons, and a lack of excess in the positive, the P, or positive one, has holes, so spaces where electrons could go, but there are no electrons there. And so what happens is, it goes from P to N. So there's excess of P, but there's holes in the N's. So what happens is it goes from P to the N, and it fills the slots. But eventually what happens is that creates a positive charge because you're losing negativity. You're losing the electrons of a negative charge. You're losing negativity, creating positive charge here, but you're filling all the slots here, creating a barrier between them based on charges. And so what that means is there can't be any more flow of electrons. There can't be any current flow. Because, as you've been told, electricity is the flow of electrons. It's the movement of electrons. But what we have to do is we have to use a gate above to establish a partial charge that turns the transistor on, and electron flow is on. Now just think about that. That's extremely instant. We turn on that charge, just a slight bit, and electrons are flowing instantly. As opposed to the switch, there are no moving parts. Electron flow is disrupted or allowed to flow by a charge that we apply instantly. And that is how modern transistors work. But instead of doing that, let's take it down to a smaller level. Let's use the electrons themselves instead of using a whole bunch of different atoms. So, let's think about an atom, for example. Let's think of a basic example. We have a nucleus and an electron going around it. In the nucleus are protons and neutrons, positively charged, because protons are positive and neutrons are neutral, no charge. Electrons are negative, which is why they're attracted. Opposites attract, just like magnets.
And love. And love.
And love.
And
Love this guy. So anyways, the electrons are going around, right? An electron can go spin
up
or
down.
spin down, right? Go spin up or spin down. What does this mean? It means it can spin this way in the most basic methods, because according to many different principles, electrons are completely different than the Bohr model as we know for basics. But for basics, you've seen a picture of atoms. The basic picture is the Bohr model is what you know of. Electrons spin around the nucleus, right? And they flow a consistent path. That's not completely true, but you'll learn more about that when you get to chemistry, and you'll learn about the different orbitals. We have p orbitals, s orbitals, and many different orbitals. And I will explain more what that means in a different video. We'll talk more about atoms and their structure in a different video. But for basics, let's think about it this way. Electrons can spin around it this way, or they can spin around it this way. This is spin up, this is spin down. So thinking about that, though, kinetic energy. Back to that. As we described, kinetic energy, the electrons are constantly moving. The atoms, in this case, are moving. But talking more about kinetic energy is also in electrons. Now, we said that kinetic energy is dependent on temperature. So, years ago, a scientist called Mr. Kelvin generated a system of temperature which has 0 as the absolute minimum temperature possible. Now, what that equates to in Celsius is negative 273 degrees Celsius is the absolute minimal temperature that is possible in the universe. Why? Because at 0 Kelvin, every single molecule, every single subatomic particle, every atom is completely still. There is no motion. There is 0 heat. Heat is from kinetic energy and vice versa. You see, they are correlating. They integrate with each other. You cannot have one without the other.
Yeah,
you see?
And the movement of what's going on at the molecular level is the foundation for all of matter, for all of existence. And if that were to stop, you would basically have an end of matter in a way. I mean, matter would still be there, but it's difficult to wrap your head around.
That's something to think about. Wrap your head around that. An electron not moving around an atom. What that means is essentially an end to covalent bonding. I mean, that is a really theoretical thing to talk about. But matter could fall apart and without kinetic energy and heat. So 0 Kelvin is impossible. It is a temperature too low to be possible. But scientists who've been working on quantum computing have made like 0.15 Kelvin is what we keep our quantum computers at. 0.15 Kelvin. That is near to nothing, near to no kinetic energy, which means that if all our electrons not moving are moving too slowly to comprehend, then the electron, spin up or spin down, no, there's no spin at all, but there is. Because 0 Kelvin's impossible. If there was 0 Kelvin, there would be no kinetic energy. The electron would have no spin. But because we have it at 0.15 Kelvin, which is it's not a measurable spin. It's too low of a temperature to measure the kinetic energy or measure the spin of the electron. Why is that something that helps us? Now, let's think about that. Spin up, spin down. Well, 0 and 1, as I have here. Spin up could be 0, or as I have there, spin up could be 1, spin down could be 0. But instead, if we have it at a superposition, as we call it, a quantum superposition, it can be both at the same time, because it is in a position between 0 and 1. It is at a quantum superposition that is not 0 or 1, but both at the same time, which makes qubits.
So it spins around in this direction and in this direction at the same time, which for us we can't do with our hands, of course. But the idea would be that, and this is actually what's actually happening. Google, they're researching this.
D wave.
Yeah, the D wave. But the thing is, with that specifically, it would not be, you would have both wrong and right answers theoretically right at the same time, and one by itself wrong. You would have to have both the electrons moving upward and downward at the exact same time in the exact same way. So basically, and every electron specifically, up and down. So what would happen?
Now that's the thing we do with qubits, and that's how qubits work. Now we can elaborate more on this, but we're just explaining the basics. Now you can lore. I am going to put some more Veritasium videos in the description, and he can show you some visuals of electrons and how that relates. He'll explain to you how this one group of scientists is working again with our silicon atoms. Why do we pick silicon atoms? Because they have a relatively stable charge. Now, he'll explain more about that. But what I'm getting at is that with these stable atoms, we have a stable charge. And so what we do is we put them down to this temperature of 0 Kelvin or close to. And then we use radio waves to push the electron into the place we want to. So we push the electron with radio waves because electrons are affected by radio waves, and we push it into a quantum superposition of both 0 and 1 at the same time. It's in between 0 and 1, so it makes it both at the same time. It's in between spin up and spin down. It's both a combination of. Now, talking more about what he was saying, you explained that you both have the right answer and the wrong answer at the same time. So you can have 0, 0, and 1, 1 at the same time. So you have a wrong and a right answer at the same time, which is why we have something called a Grover operator. And no, I'm not talking about Sesame Street.
I love that guy.
Grover operators are what allow us to determine whether it is a 0 or a 1, which is why we can't leave qubits in a superposition forever. Because when we read them, we have to measure them. We have to take them to a higher temperature to be able to measure them. And so we use a Grover operator. Now, that is something that is really hard to comprehend. I won't explain more, but essentially, the Grover operator allows us to see what the optimal combination or the right answer is. So we have both the wrong answer and the right answer at the same time, so we can try all the combinations, and we use a Grover operator to reveal what the computer has figured out, to reveal what the optimum answer is. That is what allows us to find the only optimal choice, the only right answer, or only right combination of bits, or in our case, qubits.
Instantly. Just like that, instantly. Even faster than that. I mean, really, it is such speed at a subatomic level that really, I mean, I can't do that fast.
Just think about that.
No one can.
Just think about that for a moment. Qubits are using single electrons that we move into a quantum superposition with radio waves. Because with radio waves, because at 0 Kelvin, there is no motion. There is a very slight motion, but it's unmeasurable, which is why we keep it at 0.5 Kelvin. 0 Kelvin, no motion, which is why we can't have it that low. But again, that's an impossible temperature. Anything above it is possible and allows for quantum superpositions or both at the same time. So it's completely still, right? Or almost, we say. So we use radio waves to manipulate it into the quantum superposition that we want in between spin up and spin down. Instead of using a full transistor, which has lots of electrons. It has lots of different atoms, lots of different electrons. I mean, yes, transistors are really small, but we can see them. We can see them with our bare eyes. Now, if you look at this USB stick, you can see the tiny little wires inside of it. Inside of that are some transistors. Now, why is this a good thing? Why is this cool? You see, in here, you've got lots of different atoms, lots of different electrons. Where in a qubit, you only have one electron. Much smaller scale, much more instant. No transference.
And less
It's right there.
And less information in that. A qubit is very small, so basically you would have, in here we have a lot of information, but in the qubit we would have, theoretically, nothing.
A lot more information in a certain amount of size. So not only can it do more, it's smaller. There's just so many great things about these guys. So I'm going to look again at what I have here. And so, yeah, spin up and spin down. So I think it's time for today's Cash Craze. It's time to talk about stocks, ladies and gentlemen, and I will see you after this brief break.
And kids, this is the boring part of the show, but for those of you who are smart enough, listen up. We're about to talk about your future.
And it's time to invest in the companies we'll tell you about. You see, we'll explain more. But Apple's not doing as well as they expected they would be.
iPhone X.
Kids, it's time to invest in the right companies. Pull your money out here, put your money in there. It's time to get rich easily. And we'll be right back with today's Cash Craze. Okay, everyone, and welcome to today's Cash Craze.
Welcome back. We are
So,
here.
who do we want to buy and who do we want to sell?
Yeah.
So let's pull this table back and let's do some drawing on our whiteboard. Now, those of you have probably heard about Apple. Oh, poor Apple and their innovations. Apple was so excited to release their iPhone X. Apple was so excited to tell you about all these possibilities. Now let's talk a little bit about economics, and that Apple used to be a monopoly almost on smartphones. They used to be the only seller of smartphones. Everyone wanted to buy Apple smartphones. Apple practically invented the idea. But you see, their patents ran out. And so Samsung and Google and everyone else wanted to get in with the deal. And so that's how we got other companies making smartphones instead of just iPhones. Yep. So let's talk Apple. Apple stock. Oh, poor Apple. They think they're going to take this amazing new product. I mean, yes, everyone, all these great features. The face scanner. No more passwords, no more thumbs. Face scanner. Look at your phone, and you got a password, right?
Really?
Doesn't that sound amazing? But with a price $1,000. $1,000.
$1,000.
No one wants to spend $1,000 on a phone. I mean, when you've got something else that can do practically the same job. Yeah. Yes, wireless charging is cool, but is it $1,000 cool?
No.
Not really. So, let's get into Apple. So, let's look at how Apple was before the iPhone X.
It's during the glory days when Apple was at the top of its game.
Well, we can't look back that far on
Sure.
the stocks app, but let's look at the way Apple was before the iPhone X. Poor Apple. I mean,
that was a mistake.
Not a good price. I mean, not a good choice. Okay, so I'm going to pull up Apple here. It doesn't look like I can pull up months. I'm going to try and get into... So, anyways, well, let me show you a little bit about this. You got Apple stock, right? Apple's just kind of slowly going up, flat, plateau, and then it goes up, and iPhone X, boom, everyone's so excited. That's why demand goes up. This, you should have bought your stock down here with the iPhone 7, been out for a while. Could have made a little bit of money. Everyone's so excited, and they realize this thing sucks.
It literally does.
This is not worth $1,000. Everyone's showing you, all your rich YouTubers are showing you their unboxings. And they're showing you, hey, you don't want to spend $1,000 on this. And so we start seeing some slow plateaus, and Apple goes down. Down into the depths. They go up a little bit again, and so Apple's just kind of slowly going. Now what you should have done, you should have bought down there, sold You buy low, sell high, right? That's what we tell you. So, Apple, don't be buying any Apple right now. Now, unless Apple starts coming out with a new phone that you think everyone's loving. Look online, look for all sorts of different ways. If Apple comes out with a new product that you think is going to be booming in demand, well, that's when you buy. Because everyone is starting to be excited. No one's going to buy any iPhone 7s or iPhone 8s when they hear about the iPhone 11 coming out, which is going to have all of these new capabilities that make it worth the price they charge. So, if they start coming out with a product like that, that's when you got to buy, because they're going to be down here. But then, demand is going to go up when they come out with that product. Apple stock's going to go up, company is going to have growth, but then things are going to drop if the product isn't good. So that's when you want to buy if you think it's going to be high in demand, but then people aren't going to want it afterwards. So you're going to buy low when no one wants any new Apple stuff, and you're going to sell high when everyone wants one. So that is why we had such a huge bust with Apple right now, and that's why you did not want to buy the iPhone 10, because no one else told you to buy it, stock went down. Who do you ever want to buy right now? Because remember, here's what we always tell you. We always tell you to buy low, sell high. Now, how do we know that the economy is about to change? We know it's about to change when we seem to be having technical difficulties. Okay, so obviously Apple. Now we're going to look at Verizon right now. Verizon, no. Let's look at someone that we want to buy soon.
Oh yeah.
Let's look at Dow Jones, shall we?
Now the Dow Jones, that's a very
Dow Jones is going down. Everyone seems to be going down right now. It is not a good time in U.S. economics.
Yeah.
But if we look at a more broad scale of things, I think there might be a way to fix this in the settings. My apologies, but you see there is an interesting setting that allows you to broaden out the view on your stocks app. And just explaining more about this. Who do we want to buy right now? Dow Jones isn't looking too well.
Just remember, because of the fact you can buy stock for a different, like a small piece of a company, and if you buy the right piece of the right company, you can make money. When that company goes up, you go up. But when that company goes down, you go down. So you really need to choose your battleground. You don't want to take it when it's at the highest it's ever been, because good things like that don't last forever. When they go high up, they will come down. What goes up must come down. And when they come down, I mean, really, it could be
That's the whole idea of Keynesian economics. If we look at our graph again, so let's look at Dow Jones and why you should have bought and sold. So let's think about Dow Jones and NASDAQ stock. So, NASDAQ. Let's think about this. They started seeing like a few changes here, and then it spikes up. We're seeing a couple little changes. Now, once you see a lot of movement, you start to see this. Dow Jones, this is Dow Jones. Dow Jones spikes up, and you start seeing some slow movement, and then they go down again. And they start going fast again, and then they go up. And so this is what we want to show you. Right now, it's time to buy Dow Jones. Now, right now, Bitcoin isn't doing too well either.
Yeah, the new
But right now is the time to buy Bitcoin. I mean, I swear, right now, buy Bitcoin. And right now is actually the time to buy some Dow Jones as well, because Dow Jones is low and they're about to go up. But the real company to buy right now, this is when to buy your Bitcoin. Bitcoin is about to go up. It's time to buy Bitcoin stock because they're going to go up even higher than they're at right now.
Oh yeah, this is going to be like a
You see, now this is going to take some time because it's going to be a little range of things. But here, I'm going to look at stock prices. So Bitcoin was doing so well. They were up here and then they plateaued. No, they were going down. They went up a little bit. And then, boom, slow down. And then they went up. They started seeing a couple zigzags. Had a couple little marks there. A couple little motions. And then we start to see this. And plateaus out, up, down, and it went way down here. This is where Bitcoin is now, people. Bitcoin was up here at its height not too long ago. Because those of you remember, Bitcoin used to be $500 to buy a Bitcoin, and now it's $2,000. The prices have extremely skyrocketed. Now they're up here, and then because of that, boom, slow growth down here. So now, let's look at Bitcoin. There's a lot of motion down here right now, a lot of up and down. Stock is about to go up. Everyone, it's time to buy your Bitcoin now. Watch. Bitcoin's going to skyrocket. Well, it might take some time, but Bitcoin is going to go up. And based on the looks of this graph, based on Bitcoin being way up there and coming all the way down here, it's going to go up. And it's probably going to go up quite a bit. So everyone, it's time to buy your Bitcoin, buy low. They're not doing too well right now, but we see a lot of motion, which, as we mentioned, stock is about to go up. So it's time to buy your Bitcoin. So everyone, that is today's cash craze.
Oh yeah.
And so, you know what time it is.
It's time for the wheel of technicality.
It's time to spin the wheel of technicality.
Where will it land? Up, up, up. Exhale, chef. It. Aha!
Okay. So, it is time to post on your Twitter and Instagram profiles and ask the world about today's conspiracality. What is conspiracality? Conspiracality is where we ask you to ask the world who believes in what. And today's conspiracality, did we really go to the moon?
That's the
or
question.
did NASA stage the whole thing? So, post on your profiles, ask everyone to leave in the comments leave in the comments to your picture, post a video, ask your friends, take some polls and some surveys, and see who is the one who believes and who doesn't. And so find out what percentage of people do and don't believe that we went to go to the moon. So that's what I'll leave you with today. Quantum computing, if you want us to elaborate more on any specific area, if there's any topic you want us to talk about.
Any topic.
Any topic. Anything that relates to today's innovations or last year's iPhone X.
Ooh.
So,
We'll get there someday.
ladies and gentlemen, I'll see you next time when we wake
Up universe. Let's go.
Bye! Please do remember to comment, like, and subscribe to join the Jailbreak Den. And I will see you all later. Bye!
Until next time, my friends.